Alright, let's get started with lesson 9, polar and nonpolar. In this lesson, we are going to learn how to determine if a molecule is polar or nonpolar. So far in previous lessons, we have discussed if a bond is polar or nonpolar. For instance, a bond between hydrogen and sulfur. Alright? We know that this is polar due to the difference in electronegativity values. The sulfur is going to be slightly negative because it has a higher electronegativity, and the hydrogen is slightly positive or partially positive. Therefore, we have a dipole in between the hydrogen and the sulfur, negative and positive. All right. Now, we can equally say that if we have a bond between two hydrogen atoms, that because the electronegativity of these two atoms is identical, that there's going to be basically an equal sharing of electrons and no polarity or no dipole. And therefore, this is a nonpolar covalent bond. But we can do better than that. We can actually quantify this. We can actually use some numbers to give us a better, clearer picture if the bond is nonpolar or polar or even ionic. So let's take a look at this. Let's focus on nonpolar first. If you have two atoms, again, let's say hydrogen, which both have electronegativity values of 2.1. If the difference between those two values is 0, then you have a nonpolar covalent bond. Alright, so that's a pretty easy way to determine. They have the same electronegativity values, you subtract them, it's 0, it's nonpolar covalent bond, okay? Which results in an equal sharing of electrons. Alright, so now let's turn our attention to polar covalence here. Now, it turns out that if the difference in electronegativity values between two atoms in a covalent bond is greater than 0, but less than 1.8, then it's going to be considered a polar covalent bond, and it results in an unequal sharing of electrons, which means in a situation like this, which I would write this down, that there is only a partial transfer of electrons, not a complete, but a partial transfer. But it has to be within this range to get that partial transfer. And that will then create a dipole in that bond and results in a polar covalent bond. Okay? Compare this or contrast this to an ionic bond. If the bond has an electronegativity difference that is greater than 1.8, then there's going to be a complete transfer of electrons. And that bond is therefore going to be considered ionic. So electronegativity values, the difference between them, is a quantitative way to allow us to get a better picture if the bond is nonpolar, polar covalent, or ionic. Alright? Now that we have that down, let's turn our attention now to molecules in general. Okay? To begin to understand if a molecule is polar or nonpolar, we have to look at the type of bonding that is occurring between the atoms in the molecule. One of the most important things to do first then is we have to draw the Lewis dot structure. And then once we're able to draw the Lewis dot structure, then we need to determine the shape using the Vesper theory of the molecule. And the Vesper theory, which shows us gives us an idea of the geometrical structure, is then going to help us to determine if the molecule is polar or nonpolar. All right. Now, we are going to talk about. Let's jump ahead. Let's say that we've done the Lewis dot structure. We've determined the molecule shape. Then what? Well, then what you're going to do is you're going to look at the individual bonds in the molecule. And you're going to determine if those bonds have dipoles in them. And if they have dipoles, then you're going to go ahead and draw the dipole arrows, okay? And pointing to the direction, the arrows pointing in the direction of the most electronegative atom, all right? Now, really what a dipole also can be looked at is a vector quantity. And a vector is a quantity that both has a magnitude and a direction. Magnitude and a direction. Now, what we find is when you take two vector quantities and they have the same magnitude, but they have opposite direction, then the two values actually cancel out from each other. So let's say we have a vector that goes, we have a vector that goes in one direction and a vector that goes in another direction. And they have magnitudes, let's say, of 2.1 and 2.1. So they have the same magnitude, but because they're going in opposite direction, the overall quantity value is 0. They cancel out. All right? And that's sort of how vectors work. Now, if vectors are going in the same direction, then they're additive, and you add them up to make a positive number quantity. Okay, so we're going to use vectors in our thoughts and understandings of polar and nonpolar bonds. Okay, so here we got a diagram of carbon dioxide, CO2, which has a chemical formula of that, and a Lewis dot structure, which is represented here of a carbon double bonded oxygen with another carbon double bonded oxygen. Now, the shape of this, according to Vesper, is linear, okay? And it's important to go ahead and draw the Lewis dot structure according to the Vesper shape, which is what I have here. Now, if you don't draw the Lewis dot structure according to the shape, then you're going to have some issues determining polar and nonpolar here. All right. Now, let's look at the carbon-oxygen bond. Is the carbon-oxygen bond polar? And the answer is yes. And so there is a dipole pointed towards the oxygen because the oxygen is more electronegative than carbon. And then look at the other carbon-oxygen bond, and there's a dipole, but it's going in the opposite direction towards that oxygen, which is indicated here. You can see in this diagram right there. Okay. Now, again, dipoles are vector quantities, and since the quantity of these dipoles are going to be the same, the magnitude is the same, but they're going in opposite directions, the dipole actually cancels out. So since the dipole cancels out, overall carbon dioxide is considered a non-polar molecule. All right? And that is just simply because the arrows are going in opposite directions. So if anything, just think about that. If the arrows are going in opposite directions, it cancels out the overall dipole, and therefore it is a nonpolar molecule. Now we can also see this by the electron distribution. Remember that the red color has a higher electron density than the blue. Okay? So you can see from carbon dioxide's electron density distribution that there's a dipole in this direction creating a partial negative charge and a partial positive charge there. So this is where the carbon would be, and this is where the oxygen would be, creating that bond. And then the same thing here, oxygen, so forth. You have a negative representing by the red electron density, and partial, a lot of positive charge there, a lot of negative charge there, a lot of negative charge there. So we have two dipoles that are in opposite direction, and they're going to cancel out, creating a nonpolar molecule. All right? Now let's look at water. Now water is made up of H2O. The Lewis dot structure is represented by two covalent bonds between the hydrogens and the oxygen, a lone pair of electrons. All right. You can see by the electron density distribution that up here is partially negative and down here is partially positive over here. So this is our oxygen. These are our two hydrogens forming our bond there. Okay. Now, the dipoles then are pointing up. Now, even if it's at an angle, like it's diagonal, the idea though is that both arrows are pointing up in the same direction. So because they're all pointing up, both of them, there's going to be an overall dipole going on. And so since the arrows are moving in the same direction, there will not be a cancellation in dipoles. So as shown here, water is going to be a polar molecule, and therefore the negative pole is up here and the positive pole is down by the hydrogens. So overall, water is a polar molecule. There is no cancellation in the dipoles because both arrows are moving in the same direction. All right? So again, if arrows are moving in opposite directions, the dipoles cancel out and it's nonpolar. But if the dipoles are moving in the same direction, then it's considered polar. Let's take a moment and look at a couple examples. I think that it would be helpful. So we're going to change the whiteboard here. I'm going to erase all of this. For us. And let's do a tetrahedral structure. Let's do methane, CH4. So if you draw the Lewis structure of methane, you get the tetrahedral look. All right, and let's see about the dipoles here. So there will be a dipole between the hydrogen and the carbon because there's a difference in electronegativity. It's going to be pointing towards the carbon, each one. All right. So now let's look at the arrows, okay? This arrow and this arrow are pointing in opposite directions, all right? Because they're pointing in opposite directions, this dipole is canceled out. Now, this dipole and this dipole are moving in opposite directions. One is going up and the other arrow is pointing down. So these two dipoles are canceled. So overall, methane, CH4, is considered non-polar. All right? Let's take a look at one more example here. Let's do another tetrahedral. Let's do carbon and 3 hydrogens and a chlorine, okay? If you draw its Lewis structure, it's also going to be a tetrahedral structure, like so. All right? So let's look at the dipoles. Again, you're going to have dipoles pointing towards the carbon from the hydrogens. But what about the C-Cl bond? Well, chlorine is more electronegative than carbon, so there should be a dipole towards the chlorine. All right? So let's see if the dipoles cancel out or not. So this dipole and this dipole, they're going in opposite directions. One's going up, one's going down. So this dipole and this dipole will cancel out. But what about the other dipoles? This one's going to the right, and this one is also pointing to the right. So this dipole, these two dipoles are not being canceled out, and we have a net dipole that's moving towards the right. So overall, it would tell us that this molecule is going to be polar. And so CH3Cl is a polar molecule, okay? So the idea here, the biggest thing, is to write the Lewis dot structure, determine the molecular geometry using Vesper theory, and make sure that the Lewis dot structure is drawn to represent the Vesper shape, and then determine if the bonds are polar or nonpolar, and write the arrows towards the most electronegative atom, and then determine if there's a cancellation in dipoles. If arrows are going in the same direction, then there will be no cancellation. But if arrows are going in opposite directions, then there will be a cancellation of the two dipoles, resulting in a nonpolar molecule. All right? So that's essentially polar and nonpolar. I know it's going to take some time to practice this and learn this, and we'll do that in class and as homework assignments. So for now, just get an idea of the basic understandings and prepare for a quiz over this concept, okay? And that's it for now.